Continuing with our discussion of properties of continuous functions, let's establish the following theorem. Suppose that f is continuous on the interval I, and let J equal to f of I be the range of f. Then J itself is an interval. Now, what do I mean by this theorem? Is can be illustrated using the following picture. Let's say that we're given an interval I, and we have a continuous function defined on I. Then the statement of a theorem basically says that if you look at the range of this function, because the function itself is continuous, so its graph has no breaks, then we expect that the range itself must be continuous, right? So in a sense, if this is I, then the range is J, and J must be an interval. It cannot have any breaks. How can we prove something like this? Now, clearly, of course, if the function was discontinuous, if we had a picture like this instead, so let's say I again, and maybe J is going to be like this, then in this case, of course, you do have a range that consists of two intervals, right? One here, and then another one here. So J contains two pieces, or consists of two pieces. And of course, maybe the third illustration, which is important to keep in mind, this is not an if and only if statement, because let's do the third picture. I can have a function which is discontinuous, so maybe the function will have a graph that looks like this. Right, and then the range, in this case, is still an interval. Right, so J still is an interval because the jump was a jump down. So these three cases illustrate to you that, as I said, this is not if and only if statement. If the function is continuous on an interval, then the range must be an interval. But if the range of the function is an interval, then it doesn't mean that the function must be continuous. All right, so let me just rearrange this. These pictures in the same place. And so now let's try to prove the theorem. So proof. A, if f is a constant on I, then of course j is going to be equal to is going to be a single point, right? It will be a single value that consists, the j is going to consist of a single value, which is a value of a function on the interval. And so then we're done, right? Because a single point is an example of the interval of a length 0. Let's now consider the second situation when f is not a constant. Function on I. So if this is true, then f of I, or j equal to f of I, is going to contain more than one point, right? And therefore, infimum of j is going to be less than a supremum of j, and the infimum and supremum of j, of course, both exist because j is a subset of real numbers, right? Right, so since j is a subset of R, infimum and supremum in this case also can be equal to plus or minus infinity. And supremum of j minus infinity and plus infinity, respectively. All right, very good. So next, let's observe the following. So following from this, the interval from infimum of j to supremum of j, of course, this interval is not empty, has a length greater than 0. So it has a non-zero length. And therefore, I can now choose any y in this interval. All right. And so now my goal is to show that the value of y is going to be achieved. Now, we should note here, well, before we note anything, y belongs to the interval from infimum of j to supremum of j, so then it would be tempting to try to use the intermediate value theorem, right? Because intermediate value theorem told us what? That if you have a closed interval from a to b, then if you pick any value between f of a and f of b, then there must be a value of x inside AB, where the function will attain the value of y. And this is sort of the same here. Y belongs to the interval between what looks like the smallest value of the function on I and the largest value of the function I. And the function is continuous on I. So then it seems that we can apply intermediate value theorem immediately. But the problem is that infimum of J and supremum of J actually are not necessarily possible values of your function, right? We said that J is the range of the function, but that range is not necessarily a closed interval in the sense that its infimum and supremum might not be values of the function at all. So in that sense, applying intermediate value theorem here is not going to work, right? Because it relies on the fact that we're working on a closed interval. So we will need to adjust things a little bit, and we're going to do it in the following way. So we chose any y like this. Then let's look at the infimum of J. So then y is not a lower bound on J. Right? If y is not a lower bound of J, and of course it's not because it's larger than the infimum of J. And if y is not a lower bound on J, then it follows that there exists a y1 that belongs to J such that y1 is strictly smaller than y, right? And similarly, by working with the supremum, there should exist a y2 in J such that y2 is greater than y, right? All right, so if that is the case, so now y1 is a possible value of the function. Y2 is a value of the function, actually. And so if they're values of the function, right, because y1 and y2 are both elements of J, elements of the range of your function f, that means that both values y1 and y2 are attained. So therefore, since y1 and y2 are both in J, notice that I don't know the same thing about y, right? Because y is just some number that I chose, and because that number was not an infimum, then I should, infimum of J, then I should be able to find y1 which belongs to J, meaning that y1 is one of the possible values of your function. Same for y2. So since both of them belong to J, we can conclude that there exist x1 and x2 in I such that f of x1 is y1 and f of x2 is equal to y2. Let's assume, without the loss of generality, just to fix ideas, in principle, we can always relabel things if everything works in the other way. So I'm going to assume that x1 is less than x2. Well, x1 and x2 both belong to I. x1 is less than x2, so therefore function f is going to be continuous on the interval x1, x2, because that interval is completely inside I. Well, but now we have a function f which is continuous on x1, x2. We know that f of x1 is y1 and f of x2 is y2. And we know that y is between y1 and y2. So in fact, let's write this here. F of x1 is y1. F of x2 is y2. And y belongs to the interval from y1 to y2. And now with this, the intermediate value theorem applies, right? Because I have a continuous function, a closed interval. At the endpoints of the interval, the function has values y1 and y2, and I pick a number between those two values. So then, by intermediate value theorem, it immediately follows that there exists an x in x1, x2, which is contained inside I, so x in I, such that f of x is equal to y. So with this, we can now make the following conclusion, that any value, right, because I chose y randomly between infimum of j and the supremum of j, so any value or any number y between infimum of j and supremum of j is in the range of f. And so therefore j is an interval, right? Because any value between the infimum of j and supremum of j is achieved. Maybe except for infimum of j and supremum of j themselves, but that doesn't matter because an open interval between infimum of j and supremum of j is going to be in the range. It's possible that infimum of j and supremum of j are themselves and it's in the range, but we're not postulating that here. It's possible or might not be possible. So that's it. That's a proof of this theorem. All right, so we have that. And now we will try to establish the relationship between continuity and the notion of the inverse function. So we're going to use the just established fact to do this. So our next theorem is going to be this. So let's suppose, first let me write theorem. Suppose that f is continuous strictly increasing or decreasing. Function on some interval I. If j is equal to f of I, and we know that j is an interval by the previous theorem, then f inverse is first of all, it exists, and is strictly increasing or decreasing. Continuous function on J. All right. So if I have a strictly increasing continuous function, then the inverse would exist and be also a strictly increasing continuous function. Or I can replace increasing with decreasing everywhere. All right, let's try to prove this. Well, first of all, if the function is strictly increasing, then it is one-to-one, so f inverse exists, right? F is one-to-one. On I, so therefore f inverse. In fact, let's write it this way. F goes from I to J, so therefore f inverse from J to I exists, right? So we have that, and now we need to establish two facts. Number one, f inverse is strictly increasing. Let's prove it by contradiction, so suppose not. Then what does it mean that the function is not strictly increasing? It means that I should be able to find a couple of points. There exist, now because we're working with f inverse, there exist 2 points, y1, which is less than y2. Both y1 and y2 are in J. and such that, well, if the function is not strictly increasing, then f of y1 must be greater or equal than f of y2, right? So either the function stays constant or it is decreasing on the interval y1, y2. All right, and we need to get a contradiction, and in fact it's not f, but f inverse. Okay, so f inverse goes from j to y, right? Then I'm going to denote x1 to be f inverse of y1 and x2 be the inverse of y2. Well, because f inverse of y1 is greater or equal than f inverse of y2, then we have that x1 is going to be greater or equal than x2, so this is by our assumption. And because the range of f inverse is I, it follows that x1 and x2 are both members of I. Well, if x1 is greater or equal than x2, and f inverse is x1 is greater or equal than x2, and x1 and x2 are both in I, then I can apply f to them. So then, if my function is strictly increasing, then f of x1 must be greater or equal than f of x2. Well, actually, let's look at two different cases here. Let me see. Yeah, that's fine. So f of x1 is greater or equal than f of x2, and this is because f is strictly increasing. We can actually probably split this into two statements. Let's do that. If x1 is the same as x2, then of course f of x1 is equal to f of x2. And on the other hand, if x1 is strictly greater than x2, then f of x1 is strictly greater than f of x2 because, as I just said, my function is strictly increasing. Right? So we have these two choices. So if x1 is equal to x2, f of x1 equal to, what is f of x1 and f of x2? If f inverse acts from y to x, then f acts from x to y, right? So that means that we now have the following two choices. So therefore, if x1, in fact, let me just copy this. And we'll modify this expression a little bit. Copy and paste. So if x1 is equal to x2, f of x1 is y1, f of x2 is y2, so then y1 must be equal to y2. And if x1 is greater than x2, then again, f of x1 is y1, f of x2 is y2, y1 is bigger than y2 because f is strictly increasing. Right, so this is just rephrasing the previous paragraph. Okay, so then the conclusion from this is that therefore y1 is either equal to y2 or greater than y2. Right? But if we go back to the original choice of y1 and y2, the way we chose them, we said that there should exist y1 less than y2 where something happens. So if y1 is less than y2, they cannot be greater or equal than each other, right? Because they're less. And so this is a contradiction. And because it's a contradiction, the function f inverse is strictly increasing on J. Right, so that is a proof of this fact. All right, so, and then number 2. The second fact that we want to prove is that f inverse is continuous on J. Okay, so let's see how we can do that. Let's choose if we want to prove that the function is continuous, we need to verify one of the properties of continuity. Either we have to verify an epsilon delta property of continuity, or we can verify the sequential definition of continuity. In this case, we're going to try to use the epsilon delta definition. To prove continuity, let's start from the following picture. All right. So let's say we have some interval I on x-axis, another interval j on y-axis. We have a strictly increasing function, maybe like so. So if I want to prove that my function is continuous everywhere on J, we're going to split this proof into two parts, and I'm only going to prove one. We can prove that the function is continuous at the endpoints of the interval J. That I will leave it up to you to try to prove this. And we're going to concentrate on the proof at the interior points of J. So for that, let's look anywhere inside J, pick a random point, y0 in J. So choose any y0 in between infimum of J and supremum of J. So then, if we do that, I can take y0, right, apply f inverse to it, and we end up at some point x0. So this will be f inverse of y0, and at this point we can always find some number epsilon 0, right, because if y0 is in the interior of J, then f inverse of y0 must be in the interior of J. That is a consequence of the fact that f inverse is strictly increasing, f is strictly increasing, really. So let me write this down then, because f inverse is strictly increasing, f inverse of y0 is in the interior, so it belongs to the interval, to the interior of the interval I, so therefore, because it's inside the interval I, there exists some number epsilon 0 greater than 0, such that the set f inverse of y0 minus epsilon, epsilon 0, f inverse of y0 plus epsilon 0. This interval is going to completely be contained inside I, right? That's kind of obvious because, again, f inverse of y0 is away from the endpoints. Then I can always fit an interval like this around f inverse of y0. All right, so then if that is true, we're going to try to satisfy epsilon delta definition of continuity for f inverse. So given epsilon, we should be able to select an appropriate delta. Now, the definition of continuity can be proved really, it's only relevant for small epsilon. So if it holds for small epsilon, then the function is continuous. So we're going to just use epsilons that are smaller than epsilon 0. So choose any epsilon which is greater than 0 and less than epsilon 0, and I want to find the corresponding delta. Well, so if I chose an epsilon like this, then clearly, let me make this smaller. So if I chose an epsilon like this, then immediately it follows that this subset is going to be larger than a similar subset with epsilon 0 replaced by epsilon. So if I get rid of zeros here, then the subset, then the set of numbers that I'm going to get is going to be smaller than a similar interval with epsilon 0. Okay, so if that is true, if the larger interval inside I, then the smaller interval is inside I. And if that is the case, then I can denote y1 to be, I can denote by y1 to be f of f inverse of y0 minus epsilon, and by y2 I will denote f of f inverse of y0 plus epsilon. Right, so f inverse of y0 minus epsilon and f inverse of y0 plus epsilon are 2 points inside this interval down here. So then I can apply f values to those 2 points, and I'm going to end up on y-axis. So let me see if I will be able to illustrate this. Actually, use a different color. So f inverse of y0 plus epsilon is some number here. F inverse of y0 minus epsilon is some number there. Then if I apply f to those, I will end up on the y-axis somewhere here, and this number is going to be y1, and that number here is going to be y2. Now from this picture we can see that because we have the following set of inequalities, f inverse of y0 minus epsilon is clearly less than f inverse of y0 less than f inverse of y0 plus epsilon, and f inverse is strictly increasing. We have that f of f inverse of y0 minus epsilon, let's see, not because of f inverse, but because f is strictly increasing. So sorry. When I apply f to each of these inequalities, inequality is preserved. So f of f inverse of y0 minus epsilon is less than f of f inverse of y0, in turn less than f of f inverse of y0 plus epsilon. And now if we look at our definitions, f of f inverse of y0 minus epsilon is what I called y1. F of f inverse of y0, f and f inverse cancel. This is y0, and f of f inverse of y0 plus epsilon is something that I called y2. So what we conclude then is that y0 must belong to an interval between y1 and y2. And so now I'm going to choose, I'm not going to look at just y0, but at any y that lies between y1 and y2. So any y inside the red interval on y-axis. What do we see? That if we apply f inverse to any y, or apply y inverse to any y in this red interval on y-axis, the outcome of that must end up inside the red interval on x-axis. Let's see how we can formally write that. So we consider any y inside this interval. What we know is that, the way we can write this, y is less than y2 and bigger than y1. Well, but then because f inverse is strictly increasing, if I apply f inverse to all three sides of this inequality, the inequality is preserved, right? Because the function is strictly increasing. So f inverse of y1 is less than f inverse of y less than f inverse of y2. Well, but what is f inverse of y1? You take y1, you apply f inverse to it, you end up at this endpoint of the red interval. And what was at the red endpoint? It was defined as f inverse of y0 minus epsilon. To see that, so this is our y1. I'm going to copy that. F inverse, oops. I'm going to note f inverse of y1 is the same thing as f inverse of f inverse of y0 minus epsilon. F inverse of f cancel out. You get f inverse of y0 minus epsilon. And likewise, if you take f inverse of y2, that's f inverse of f inverse of y0 plus epsilon. These two, f inverse and f, cancel each other out, and you end up with f inverse of y0 plus epsilon. And so from the inequality that I got here, and from my computations just now, then we have that f inverse of y0 minus epsilon is less than f inverse of y less than f inverse of y0 plus epsilon. Well, and that means that if I subtract f inverse of y0 from all three sides, minus epsilon is less than f inverse of y minus f inverse of y0, and this is less than epsilon. And of course, writing that, this can be written by using the absolute value as f inverse of y minus f inverse of y0, that this quantity is less than epsilon. So as long as y lies between y1 and y2, then f inverse of y minus f inverse of y0 is less than epsilon. So, and that is what I want. I want, because I'm trying to prove continuity of the function f inverse, this is what I'm going to get as long as y minus y0 is less than delta.